Okay, I'm going to go through the finger tapping and visual task analysis in NIRS Lab. So this is NIRS Lab. The icon is here. First, we load the data. Data is stored in the C drive, in the NIRS folder, the data folder, and then at the date of the recording. If there were multiple recordings in that day, they'll be iterated. You can see the size and the date, the time of the recording. This might help differentiate between subjects if there are multiple subjects recorded in the day. So we'll go with the first one. We'll override this time, but usually if you're revisiting a analysis, you won't have to. So usually you'll put a 1 here. And once we finish loading, we will set markers to edit the event file. So the duration for the visual task is 30 seconds, and for the finger tapping task is 10. The condition 32 is visual task, and finger tapping are left 64 and right 128. So to assign duration, first we do 30, 10, 10 for the conditions in order. So it's visual, left, right. Then we can rename the conditions to the appropriate name. So 32 will be visual. Click OK. 64 will be left. Click OK. 128 will be right. And click OK. So now we save and close. Oops. Okay. Next, we run through the pre-processing pipeline. First, we truncate. Here we can clip off the beginning and end if there's a long strip of recording before or after the experiment is actually taking place. So, for example, here we'll cut the beginning session to the first 30 seconds before the first marker, and that will trim off that noise. We can save and close. We'd also be able to remove some of this noise, but when you do remove noise between the tasks and afterwards, keep in mind that the last task will usually have some extra data that it would need for block averaging and analysis, so sometimes it's just better to leave this noise in. We can save and close. Next, we remove discontinuities. With this button, it does it for you. Save and close. We won't be interpolating for this pipeline, but for the pipeline in NIRS Toolbox, which I will create a new tutorial for, I'll describe that in greater detail. For now, we will remove bad channels with this check data quality. Bad channels will be detected based on gain settings and cross-validation error percentage. So for cross-validation, we will set it pretty high. So with the default setting, we have 72 bad channels, which means that gain is either above 8 or the cross-validation error is particularly high. So to allow more channels in, because there seem to have been a lot of bad channels, we'll increase this to let more noise in. At 30, we have still 20 bad channels. Maybe, yeah. We see that the error is usually among the bad channels above 40 or 50, so we probably won't want those in this case. There are some particularly bad channels. So we'll stick with this and see how it goes. We can remove spike artifacts. If there is a shift in the cap, you may see a jump. This is usually removed by filtering, but Other spike artifacts can be removed using this tool. Next, we apply the filter. If you want to change any of the configuration parameters, you can do that here. We'll use default. Next, we save and close. To compute the hemodynamic response, we look at this plot. Generally, the default is configured correctly. It pulls from a laser configuration or a LED configuration file. The wavelengths should be what the LEDs are configured to, but you can double check here. We'll save and close. Click Compute Hemodynamic States. Now that that's finished, we can plot in a few different ways. First, we'll run through block averaging within subject. We can view different combinations of data. So in this instance, we'll look at both oxy and deoxy blood. Look at only left and right conditions. And you can refresh this plot. However, since the scales and figures are so small, it doesn't really help. So we'll look at a channel in the right hemisphere. Again, or to explain it a little bit better, these channels in the front are on the top are front, left hemisphere, right hemisphere on the right, and occipital in the back. In this figure, we see that for the left finger tap condition in the right hemisphere, we have a spike, an increased oxy. I'm sorry. In the right hemisphere, for the left condition, we see a decline in oxy and an increase in, or decrease in oxy for the left-hand condition and an increase for the right-hand condition. And with the deoxy signal, for the left-hand condition, we have an increase, and for the right, we have a decrease. Keep in mind when you're looking at these, the experimental design can get lost in here. So for the first 10 seconds is when the finger tapping is actually occurring. For the 15 seconds following that is a resting period. And then after that resting period is the beginning of the next task. So when you're looking at this figure, keep the experimental design in mind. For the visual task, we would see 30 seconds of the actual activity, and then 15 seconds of resting period. So we'll close this. You can also look at matrix mapping, gain set viewing, sec viewing. These can be helpful depending on the experiment. You can save the figures, or you can take screenshots. Another way of mapping the hemodynamic response is through this plot, which will allow you to view it in 2D and 3D formats and rotate and animate. So, for example, we will look at the we'll see if this works. Okay, so we'll look at oxygenated blood and the channels that we have access to. So the channels that were not removed during the bad channel selection process. As we can see, maybe we'll see better from the 2D. There are a number of channels in the occipital lobe that are missing. So this might be detrimental to the classification, or rather for the modeling on the visual task. If we had good channels back here, it may perform better for visual task differentiation, and likewise in the motor cortex. The more good channels in this region, the better the model will likely perform. You can also animate this and play it over time. It's kind of nice for visualizing, but it's not particularly helpful from a statistical standpoint. So to get into the statistics, we'll run a general linear model using SPM. This block averaging tab is helpful for comparing across subjects, which we are not doing in this tutorial. So to run the GLM, we open SPM level 1. SPM level 2 is for group analysis. We load the data in the same way that we loaded the data on this tab. So we select the NIRS-info MATLAB file. We save it to the default. We set the GLM parameters. The most important parameter is this, the NIRS-lab condition file. So this will help differentiate from between the conditions. And confirm that this looks all correct. So this is the visual task, left and right. I usually do DCT temporal filtering. It's sometimes helpful, but it really depends on the experimental design. In this case, we're going to be using probably a different pipeline in the NIRS toolbox to do the analysis, so we'll set the parameters there. In the meantime, we can use this kit for producing reporting and analysis on these. So you're welcome to play around with these configurations and see how it affects the output. So we'll save this to the default location. Next, we'll estimate the GLM coefficients. Once this model is done running, we can view here. So first we'll look at the beta coefficients to see which channels are most important in the model. And as we can see, there's a couple channels with a high beta coefficient in the motor cortex. Not too much going on the occipital lobe. So let's see how the model actually performed. We will threshold the t-score with a p-value of 0.05. First, we set the contrast. We'll start by looking at the right compared to the left condition. And we'll view the significant channels. We can see there's not a lot of activity in the motor cortex in this model, so likely it had not performed very well. We can dive deeper into the statistical output, but based on these findings, we won't have much to report. I'll reverse the contrast to see if we see something more. Sometimes the left condition compared to the right has better output rather than vice versa. We see in the motor cortex for this condition there is a significant region that's likely due to the experimental design for the right-hand condition as compares to the left, which is good. Lastly, we'll look at the visual task. And again, this one does not look very good. Likely it's because of those missing channels in the occipital lobe. but deeper statistical analysis might provide you with more information. So this is the old pipeline. We can do preliminary analysis, view the quality of the data, pull some statistical results, and do some cross-subject analysis in this tool. Alternatively, I've written some scripts for this nearest toolbox, sort of Bitbucket, made by Ted Hubert. This is built in MATLAB. There's a lot of functionality that will be more helpful than in NIRSLab. This tool is not currently being developed by NIRX. They're moving to the nearest toolbox as well. So I will share the script that I made for this analysis, and in this environment, we'll likely move forward with the processing, especially for the language task. So if you have any questions, please reach out to me. I'll share my email, and I hope that was helpful. Take care.